Ever wondered how rockets navigate through space? It's all about vectors. In this new playlist for classical mechanics, we're kicking things off by tackling fundamental vector operations that are crucial in physics. In today's video, we have a 2-for-1, problems 1.1 and 1.2. And in 1.1, we're given two vectors b, which is equal to x hat plus y hat, and c equals x hat plus z hat. We're tasked with finding their sum, their scaled sum, dot product, and their cross product. In problem 1.2, the two vectors are given as b equals 1, 2, 3 and c equals 3, 2, 1. Remember that these statements are just a compact way of giving you the components of the vectors. And much like before, we were tasked with finding their sum, their scaled difference, the dot product, and their vector product or cross product. Now, the real difference between these two problems and the two things that'll keep coming up is the notation. And in 1.1, we use the unit vector notation, which removes the ambiguity of which orthonormal bases we use, but it is cumbersome. Now, in problem 1.2, a compact vector bracket notation removes this issue, but doesn't tell us what bases we're in. Now, this becomes a problem when we're moving from bases such as Cartesian to spherical or cylindrical. We don't have that. We don't have what bases we're in the vector brackets, but we'll have to imply that from the geometry. Whereas we could write them out in the unit vector notation, but at the cost of being cumbersome. So we'll cover both and see whatever you like. One word of warning though, parentheses often indicate points as we've seen in many math classes. So instead, I'll opt for angle brackets, which we will see in just a second. So to kick things off with problem 1.1, we can write the given vectors in the following way. That way we can bridge the gap between unit vector and angle bracket notation. So b is given as x hat plus y hat. Now what's multiplying x hat and y hat is just 1. So we put 1 in both the x and y spaces respectively, and we don't have anything in the z hat, so we put a 0 there. Again, these are the vector brackets or angle bracket notation, and that's a little more indicative that we're dealing with vectors as compared to parentheses, which tells us that it could be a point in space. So just a little distinction there. C was given as x hat plus z hat, and we could write that in vector bracket notation. We have 1 unit in the x direction, 1 unit in the z direction, none in the y direction. So our first thing to do was to add the two vectors. So this is vector addition, and we could utilize equation 1.4, which is given up here. What this equation tells us is that for each vector, we need to add their components in the same element space, meaning x to x, y to y, z to z. So, following this lead, b plus c, we break them down into vector components, and we add them component-wise. 1 to 1, 1 to 0, 0 to 1, and that gives us a new resulting vector of 2, 1, and 1. Now, if you had taken an introduction to physics classes, you saw that a vector had a length and a direction, and then you had to break them down into these components before adding. Here, we're just doing it in component-wise before having, and we don't even have to break it down. But in the next part, we had a scaled version of this addition. So this is multiplication by a scalar and vector addition. So we could utilize equation 1.5 and then 1.4. So 1.5 tells us that the scalar c multiplied to the vector needs to be distributed to every single component. And then we could add them up using 1.4. So taking the lead, 5 times b plus 2 times c. See our 5 in our component form vector, 2 in our component form vector. We distribute 5 to every component. 5 times 1, 5 times 1, 5 times 0, 2 times 1, 2 times 0, 2 times 1. From here, the result is two new vectors. So we get a 5, 5, 0 vector and a 2, 0, 2 vector, which is just a scaled version of the original vectors that we had, hence scalar multiplication. Now from there, we know that these two vectors can be added component-wise, just like we saw here. So 5 to 2, 5 and 0, 0 and 2, leaves us with a new resulting vector of 7, 5, 2. Not too bad. So if you're finding this breakdown helpful, give it a thumbs up and share it with others who might benefit from it as well, especially with the new semester kicking off. Now, we have to get to the products of this part. So this is a dot or scalar product. And since we're in component form, we can utilize equation 1.7. So here's 1.6, 1.7 combined, both definitions of dot product. We'll cover this one in just a second. But here, since we're in component forms, we have to multiply each component to the corresponding same component and add them together. So how we see this, B dot C, component form, 1 to 1, multiply, add, 1 to 0, right there, and then 0 to 1, multiply, and add them all together. This leaves us with a grand total of dot product equals 1. Now, its counterpart, the cross or vector product, since we're in component form, we could use the equation 1.9, which is in a determinant form. And from here, we see that B cross C, this determinant becomes a little nasty. And if you're not comfortable with determinants, be sure to check out video 8.8 in the linear algebra appendix playlist, which covers this in a large amount more depth than what we're going to do here. But nonetheless, in the typical cross products, we expand about the first row. So x hat, y hat, z hat are the cofactors with plus, minus, plus, and then the minor determinants there. Then we'll crisscross them and evaluate the 2x2 determinants. So we see all the work laid out there. Simplifying these, we end up for the x hat 1 minus 0, 1 minus 0, and 0 minus 1. So those result in new components of 1, negative 1, negative 1. Now these are in unit vector notation, so switching them to angle bracket notation very much keeps it clear and tells us that the new vector or the result is a vector versus this result is a scalar. So hence the scalar product name there and the vector product name here. Now these are the algebraic forms, and we'll explore their geometric counterparts soon. So be aware that there's always more definitions to come, but for these physical vectors, these are kind of the mechanics you're going to have to use on them. Now that we've seen this kind of layout, we can speed run the next one. Since we're already in component form, we just write it out so we could see the unit vector form and bridge the gap between the two. 1x hat, 2y hat, 3z hat, 1, 2, 3. 3x hat, 2y hat, 1z hat, 3, 2, 1. So let's get their sum and differences chugged out. Add them together, tells us that we're doing component-wise addition, so we end up with the resulting vector of 4, 4, 4. Scaled difference, we have to multiply the 5 in and the 2 in first, gives us two new vectors. And just like addition, we can take the difference component-wise. So 5 minus 6, negative 1, 10 minus 4, 6, 15 minus 2, 13. So we're good to go there. Now on to the products. Dot product, which will be our savior throughout this class. We see that we have dot product of 1, 2, 3, 3, 2, 1. Take component-wise, 1 and 3, 2 and 2, 3 and 1, leads to 10. Not too bad. Now the nasty one, the cross product, just takes a little bit more work. Expand, crisscross, 2 to 1, 3 to 2, and simplify. We see that upon simplification, we get 2 minus 6, and then minus 1 minus 9, plus 2 minus 6. So we get negative 4, 8, negative 4 in unit vector notation, and negative 4, 8, 4 for the vector bracket notation. Again, be aware, different notations, but same idea. Now remember, practice makes perfect. So try these operations with different vectors to solidify your understanding, because they will come up over and over again in this book. In the upcoming sections, we'll explore how these vector operations are applied in real-world scenarios, so it's best that we get a good grasp on what's going on with these before we dive into the actual heart of the book. So if you're passionate about understanding classical mechanics, hit that subscribe button so you don't miss my next video in this series. A huge thanks to my Patreon supporters. Your backing enables me to create these in-depth physics content and videos. Your support truly drives this channel forward. Want to support our physics exploration? Check out the link in the description below and join the scientific journey. As always, thank you for watching, and until next time, stay curious.